In this lab, I'll be applying Newton's second law to an object moving in the same direction at the same speed, and then extracting motion data from a video of the object. Newton's second law: net force equals mass times acceleration, or net force divided by mass equals change in velocity over change in time. In order for Newton's second law to explain an object with constant velocity, acceleration must be equal to zero, which means that the net force on the object is equal to zero. To begin this lab, I videoed a kickball being rolled on concrete at what is predicted to be a constant velocity motion. I chose to use a kickball because the spherical shape and smooth surface allows it to roll easily across the ground. I uploaded the video into Tracker software and analyzed the motion of the ball by developing an experimental model. I set the axis so that the kickball will be traveling horizontally in a positive x direction and the zeroed y direction. If I flip the axis, the ball would be then moving in a negative x direction, which would change the slope of the position versus time graph. The ball would still move in a straight line at the same speed, but it will be traveling in a different direction. As you can see, the kickball moves at a constant velocity. Tracker provided position versus time data for each frame, which is shown in the position versus time graph. The graph has a positive straight line with a constant slope, which shows a constant velocity. I recorded the length of the observation in seconds, the ball's mass, the initial position provided by Tracker, and the initial velocity, which was found by using the formula change in position over change in time for the first two data points in Tracker. I then constructed a computer model of the ball's motion by plugging these values into my VPython code at these given areas. As discussed before, the net force of zero would predict a model of an object moving in the same direction at the same speed. As you can see at the bottom, I also added formulas for Newton's second law and the formula for finding a new position so that the code could accurately model the ball's constant velocity. When I run the code, I get the predicted model of the motion of the ball. The trajectory of the ball with constant velocity in this predicted model is very similar to the actual path of the ball in the video shown in Tracker. I extracted the position versus time data from my experimental model in Tracker and the position versus time data from my predicted model in VPython and compared the results in one position versus time graph. The solid red line represents the predicted positions, and the dotted blue line represents the observed positions of the ball at various times. The experimental position versus time graph was almost exactly the same compared to the predicted position versus time graph. There were some marginal deviations between the two graphs, which was most likely caused by the slight change in speeds of the ball not rolling on a perfectly flat surface. The force of friction and the force of air resistance are acting on the ball in the negative x direction. However, the force I initially applied to the ball by pushing it across the surface in the positive x direction negates the frictional force as well as the force from the air. The normal force in the positive y direction also negates the gravitational force in the negative y direction. Because of this, I can say that the pushes and pulls added together give zero net force in the motion of the kickball across the ground. This is why I was able to observe the kickball moving at a constant velocity during the short time interval of 0.7 seconds. If I had analyzed a larger time interval, such as 1.5 seconds, I would expect the ball to slow down as time passes because the force of the initial push is smaller than the forces of friction and air resistance. Overall, my experimental data of the kickball was very close to my predicted data of the kickball. Thus, the kickball was moving at a constant velocity due to Newton's second law. To improve the experiment, I would choose a smoother and flatter surface to roll the ball on so that the experimental model will be even closer to the predicted model.